Last time we were discussing buffers, and we saw that a buffer has a mixture of both a weak acid and its conjugate base, or a weak base and its conjugate acid. And what's really great about buffers is they can neutralize any added acid or base within reason, and that will maintain the pH of the solution. Now, one thing that we should discuss about buffers is what's called the common ion effect. So in a weak acid solution, so let's say we have HA and it's reacting with water, and in that process we're going to produce the conjugate base of the acid and some hydronium ions. If we add a salt that contains this anion, A-, so let's say we're adding sodium A, which is the conjugate base of the acid, that's going to shift the position of equilibrium to the left. And this is according to Le Chatelier's principle. If you add more product, then things are going to shift back towards reactants. So everything's going to shift left. Now, not only is this going to create more of the original acid, but this is going to lower the hydronium ion concentration, because remember, if we add more of the conjugate base, then we're going to start a reaction between A- and the hydronium ion. So this is going to, again, lower that hydronium ion concentration. So the solution is going to become more basic. So as the concentration of H3O plus decreases, that's going to increase the basicity of the solution, and so the pH of the solution will also increase. So again, this is the common ion effect. We have HA and A- in solution. So we have a common ion. So we can actually see this in our, or in this figure. So if we were to measure the pH of acetic acid by itself, we would find the pH is about 2.9. And then if we measured the pH of sodium acetate by itself, the pH would be about 8.9, so basic. And then if we have a mixture of the two, the pH is around 4.7. So having a common ion present in solution is going to decrease the acidity of the solution. So you'll notice we went from 2.9 to 4.7. Okay. Now, last time we went through a problem where we calculated the pH of a buffer solution, and we used our typical steps. So we wrote out the equation, we made an ice table, and then we input the initial concentrations, and we eventually wrote out the equilibrium expressions for each. And then we wrote out the acid ionization constant expression. And then we solved for X, which was the concentration of the hydronium ion. Oh, my dog is drinking water in the background. Sorry if you can hear that. So an equation derived from the Ka expression that allows us to calculate the pH of a buffer solution is called the Henderson-Hasselbalch equation. And this is going to be an easier way to calculate the pH of a buffer solution. So the equation is shown down below, and we can see that the pH of a buffer is equal to the pKa plus the log of the concentration of base over the concentration of acid. Now, this equation only works if the x is small approximation is valid. So remember previously, we would solve for x, and then we would assume that x was small. So remember, x is the change in concentration. And we always wanted to check that assumption to make sure it was valid. And we said that if the value of x over the original concentration of acid times 100 was less than 5%, then our approximation was valid. So this is a really easy way to solve for the pH of a buffer solution. Now, it doesn't always work. Sometimes we do have to use the quadratic formula and solve that way. But typically the Henderson-Hasselbalch equation can be used. So let's actually go through the derivation of the Henderson-Hasselbalch equation. And remember that this is derived from the pH and the Ka value. So let's say we have our generic acid chemical reaction here. So we have our acid and it's reacting with base, and we're producing hydronium ions and the conjugate base. And if we write out the acid ionization constant for this equation, again we have the concentration of products over the concentration of reactants, so just like we've always done. And then we're going to rearrange this equation to solve for the concentration of hydronium ions. So once we rearrange that equation, we'll see that the concentration of hydronium ions is equal to the Ka value times the concentration of acid over the concentration of base. Okay, so now the next thing we're going to do, we're going to take the logarithm of both sides and then expand. So we have our expression for the concentration of hydronium ions, and now we're going to take the negative log of both sides. So on the left-hand side, we have the negative log of the concentration of hydronium ions. And on the right-hand side, we have the negative log of Ka times the concentration of acid over the concentration of base. And remember that if you have a logarithm of two items that are multiplied by each other, we can actually expand that, and we can say that we have the log of our first item plus the log of our second item. So on the right-hand side, we're going to expand this logarithm expression, and we end up with the negative log of Ka minus the log of the concentration of acid over the concentration of base. So some of these expressions should look pretty familiar. For instance, the negative log of hydronium ions is our pH expression. And then the negative log of Ka, that is our pKa value. And then the rest of the equation, let me erase this line here, is negative log of the concentration of acid over the concentration of base. And we're taking the log of that whole thing. So this doesn't quite match the Henderson-Hasselbalch equation just yet. There's one more thing we have to do. So again, we have that pH is equal to pKa, and if we flip our log expression, so instead of acid over base, we have base over acid, we also flip the sign. So you'll notice we went from negative log to positive log. And that will give us our final expression. So the pH is equal to pKa plus the log of the concentration of base over the concentration of acid. And again, we're taking the log of this whole thing here, base over acid. So that's our Henderson-Hasselbalch equation, and sometimes it's nice to see where that comes from and how it's derived, so it's not just thrown at you and you have to trust it. So now, if we want to use that Henderson-Hasselbalch equation, remember that it really only works when we assume that x is small and we verify that x is small. Now remember that the x is small approximation will work when both of the following are true. So we need the initial concentrations of acid and salt to be pretty concentrated, so not very dilute. And then we also need a Ka value that's fairly small. Now, because we're typically working with weak acids and weak bases in buffer solutions, usually the Ka value is pretty small. But additionally, we need significant amounts of both the weak acid or the weak base and the other component. So the initial concentrations will also be pretty high. So again, the Henderson-Hasselbalch equation can usually be trusted for buffer solutions, but we always want to double check. So down below, we can see that for most problems, the initial acid and salt concentrations should be over 100 to 1,000 times larger than the value of our acid ionization constant. Okay, so let's go through an example so we can actually see how this Henderson-Hasselbalch equation works. Okay, so let's calculate the pH of a buffer solution that is 0.05 moles per liter in benzoic acid. And the formula for benzoic acid is HC7H5O2. And then we also have 0.15 moles per liter of sodium benzoate, which is NaC7H5O2. So you'll notice this common ion here. And then for benzoic acid, the Ka value is 6.5 times 10 to the negative fifth. Now this example is also in your textbook. And what's really nice is in your textbook, it goes through the previous method we used, and it uses the Henderson-Hasselbalch equation side by side. So you can see that you get the same results whether you use our previous method or if you use the Henderson-Hasselbalch equation. So it's just kind of nice to see that the Henderson-Hasselbalch equation does work. Okay, so let's use the Henderson-Hasselbalch equation. Let's write it out first. So we need to identify our base and our acid. So the base will be negatively charged, and then the acid will have a hydrogen attached. So the base is sodium benzoate. And the acid is benzoic acid. So it's kind of given away in the name. Now, we don't have a pKa value, we just have a Ka value. So let's rewrite this equation so that we can solve for the pKa. And remember that if we want to solve for pKa, that's equal to the negative log of the Ka value. So now let's plug in all of the values that we have. Okay, so we put in our Ka value, and then we put in the concentration of the base over the concentration of the acid. And you'll notice that the units for concentration cancel. And remember, again, we're going to take the log of that full expression there, so 0.15 over 0.05. All right, so now let's plug this into our calculators and see what we get. So for the first part, the pKa value comes out to be 4.187. And then the other part of our expression comes out to be 0.477. Now you'll notice that we do have two significant figures for two of our values, and then the other value has three significant figures. So we want to limit our answers to, let's see, 2 sig figs. All right. So now at the end, if we add those together, we should get 4.66. Okay. Oh, sorry. So now let's check that our answer makes sense. Okay. So now we said that the x is small approximation is valid if the x value divided by the original concentration of acid is less than 5%. Now, x is usually equal to the concentration of hydronium ions. So let's determine the concentration of hydronium ions, and we can do that using the pH value that we just calculated. So remember that the concentration of hydronium ions is equal to 10 to the negative pH. So we'll plug in 10 to the negative 4.66. So that gives us a concentration of 2.2 times 10 to the negative fifth moles per liter. So let's compare that to our original acid concentration. That was 0.05. And then we'll multiply that by 100. And we should get 0.044%. So that means that our approximation is valid, and that means that our pH is 4.66. Okay, so let's work on worksheet problem 2. We're going to calculate the pH of the solution that results from each mixture. So in our first mixture, we're adding 150 milliliters of 0.25 molar hydrofluoric acid to 225 milliliters of 0.3 molar sodium fluoride. So that's our buffer solution. And then our second solution contains 175 milliliters of 0.1 molar ethylamine with 275 milliliters of 0.2 molar, the conjugate base. All right, so let's do part A together, and then I'll let you work on part 2 before we go over it together. Now, if you do want to try both of these on your own, you can always pause the video. So let's start with problem A. Now, we're not told the concentration of hydrofluoric acid and sodium fluoride in the total buffer solution. We're adding a certain amount of hydrofluoric acid to a certain amount of sodium fluoride. So the first step here is to figure out what is the new concentration of hydrofluoric acid after it's added to sodium fluoride. And also, what's the new concentration of sodium fluoride? So let's start by determining those concentrations. Okay, so to determine the concentration of hydrofluoric acid, we're going to first figure out how many moles of hydrofluoric acid we have. So we're going to multiply the volume by the molarity, but first we need to convert milliliters to liters. And then we will be able to cancel liters with liters in the concentration. Oh, okay. Oh, so actually, let me change this description here. We're not solving for concentration just yet. We're solving for moles of HF. Okay, so milliliters are going to cancel with milliliters, liters cancels with liters, and we'll end up with moles of hydrofluoric acid. All right, so I got 0.0375 moles of HF. And then let's determine the total volume of the buffer solution. So we're just going to add the volume of HF with the volume of NaF. So we had 150 milliliters plus 225 milliliters. So that gives us a total of 375 milliliters. And then we can figure out that value in liters, since that's what we need for concentration. All right, so that would equal 0.375 liters. All right, so now we have the components we need to calculate the concentration of hydrofluoric acid in this buffer solution. Okay, so this would equal 0.0375 moles of hydrofluoric acid over 0.375 liters. So that's going to give us a concentration of 0.1 moles per liter. All right, so this was the long way to figure out the new concentration. Some of you might be thinking, why didn't we just use the dilution equation? M1V1 equals M2V2. You can. So let's do it that way. All right, so our initial concentration of hydrofluoric acid was 0.25 moles per liter, and our initial volume was 150 milliliters. And then we're going to solve for the new concentration, M2, and our final volume was 375 milliliters. All right, so if we solve for that, we should also get 0.1 moles per liter. And that's our concentration of HF. Okay, so now seeing that we can just use the dilution equation and it makes life a lot simpler, let's do the same thing for NaF. All right, so the original concentration of NaF, sodium fluoride, is 0.30 moles per liter. The initial volume is 225 milliliters. And then we'll set that equal to the new concentration times the final volume, which is 375 milliliters. Okay, so if we solve for M2, we should end up with a concentration of 0.18 moles per liter. So that is our new concentration of sodium fluoride. So now that we have the concentration of our acid and the concentration of our base, we can plug that into the Henderson-Hasselbalch equation. Okay, we're missing one thing though. We do need the Ka value for hydrofluoric acid. So if you look in the back of your textbook, you'll find that the Ka value for hydrofluoric acid is 6.8 times 10 to the negative fourth. So I'm going to rewrite this equation so that we can solve for the pKa, and that's just equal to the negative log of the Ka value. Okay, so now we can solve for the pH. I'm just going to plug in the Ka value, and I'm going to plug in those concentrations. So remember that the base was sodium fluoride, and that had a concentration of 0.18 moles per liter. And then the acid was hydrofluoric acid, and that had a concentration of 0.1 moles per liter. All right, so putting this all together, the pKa value should be 3.167, and then the other part of our expression should be 0.255. So that is equal to a pH of 3.42. Now, always remember to check that your approximation is valid. So first we're going to solve for the concentration of hydronium ions using the pH value that we just determined. And we find that the concentration is 3.8 times 10 to the negative fourth. And then we're going to compare that to the original acid concentration, which was 0.1. And then we'll multiply that by 100, and we should get a value of 0.38%. So that means that our approximation is valid. Okay, now for part B, this one is a little bit trickier. Because we don't have an acidic buffer solution, we have a basic buffer solution. So again, in this one we have 175 milliliters of 0.1 molar ethylamine, which is a base, and it's a weak base. And that's mixed with 275 milliliters of 0.2 moles per liter of the conjugate acid. All right, so for this particular problem, we're going to use a Kb value because that is what's actually found in our tables in the back. So the Kb value of the weak base is, let's see, where are my notes? Ah, there they are. It is 5.6 times 10 to the negative fourth. Okay, so let's start by figuring out our new concentrations for the base and the acid once they're mixed together. And again, we can use M1V1 equals M2V2. That'll make things much easier. So let's start with our base. So the initial concentration is 0.1, and the initial volume is 175 milliliters. And then we'll set that equal to the new concentration times the final volume. So if we add 175 to 275, we should get a final volume of 450 milliliters. So M2, our new concentration, once we solve, should equal 0.039 moles per liter. So that is our new concentration of our base. All right, now let's do the same thing for our conjugate acid. So this conjugate acid has a chloride ion attached, so really there's a positive charge on the conjugate acid, and that chloride is just there to balance the charge. Okay, so the initial concentration of our acid was 0.2 moles per liter, and the original volume was 275 milliliters. We'll set that equal to our new concentration times the final volume, which was 450 milliliters. So if we solve for M2, we should get a concentration of the acid that's equal to 0.12 moles per liter. Okay, so we have our two concentrations. So now let's write out the Henderson-Hasselbalch equation. And we've run into a bit of a snag because remember we have a Kb value, but we don't have a Ka value. So remember that Ka times Kb is equal to 1 times 10 to the negative 14th, which is our Kw or ion product constant. So we can solve for Ka using this equation. And we said that our Kb value was equal to 5.6 times 10 to the negative 4th. All right, so when we plug that into our calculators, we find that the Ka value is 1.79 times 10 to the negative 11th. So this is a really weak acid. Okay. So now we can plug that into our Henderson-Hasselbalch equation. All right, so I'll rewrite this so that we solve for pKa. So now I'm just going to plug everything in. So we said that the Ka value was 1.79 times 10 to the negative 11th. We said that the concentration of our base was 0.039, and the concentration of our acid was 0.12. So the Ka value would be 10.75, or the pKa value, and then the other part of our expression is actually equal to negative 0.488. So we're going to subtract 0.488 from 10.75, and we'll find that our pH for this buffer solution is 10.26. And that makes sense because this is a basic pH value and we have a buffer solution that consists of a weak base and its conjugate acid. However, we are going to check our approximation again. We always want to do that. So let's check, in this instance, the concentration of acid. So that should equal 5.5 times 10 to the negative 11th. And then we're going to check that against the original concentration of acid. So that's 0.12. And we get a percentage that's really small. So it's 4.6 times 10 to the negative 8%. So I would say our approximation is valid. Now, you could also check the concentration of hydroxide ions, since this is a basic buffer solution, and compare that to the original concentration of the base. But it should work out that the Henderson-Hasselbalch equation is valid. All right, so we'll stop the lecture there today. Hopefully this helped a little bit now that we have a new way to solve for the pH using the Henderson-Hasselbalch equation. And I will see you in the next video.